Hello everyone. We're going to continue our discussion on brain trust. In our previous discussion, we have identified the difference between global coordinate system and local coordinate system. We were able to identify the degrees of freedom. We were able to identify also joint load vectors as well as reaction vectors on a plane trust. Now we're going to discuss member stiffness relation in the local coordinate system. In the stiffness method of analysis, the joint displacement D of a certain structure due to an external loading P are determined by solving a system of simultaneous equations expressed in the form P is equal to S times D. Now to take note that our S is our structure stiffness matrix, our P is our joint load vectors that we have identified a while ago, our D is your degrees of freedom that we're going to solve. The stiffness matrix for a member expresses the forces at the ends of the member as a function of the displacements of those ends. In this section, we derive the stiffness matrix for the members of the plane trusses in the local coordinate system. So for this illustration, we're going to establish the member stiffness relation. So for us to establish the member stiffness relation, let us try to have this illustration or this figure of a plane truss. So this is a plane truss subjected, of course, to an external load. So that we could establish the member stiffness relation, let us focus our attention on an arbitrary member M of the plane truss as shown in our figure A. So we're going to focus our attention on member M. So if this truss is subjected to external load, M will deform and internal forces are induced at both ends of the member. So let us try to establish now the member stiffness relation. So let us isolate member M. If you're going to isolate member M, you have now figure B. You have isolated member M, of course. As we isolate member M, we have now illustrated the displaced position for our member M. There's a displaced position due to the external forces. Of course, basically for this member M, it will have two displacements. It has translation along the x and y direction as needed to specify the displaced position of each end of member M. So member M will have a total of 4 member end displacement and will have a total of 4 member end forces. So if you're going to observe in our illustration here, we have member M. There would be 4 member end displacement and there would be 4 member end forces. Member end displacement in the local coordinate system is designated by letter U, and member end forces in the local coordinate system is designated by letter Q. So if we're going to illustrate here our member end forces for member M, we're going to have there would be 2, as mentioned, there will be 4 member end displacement. So for each end of the member, there will be 2 member end displacement. So the 2 member end displacement, you're going to have along x direction and along y direction. So you're going to number first along x direction. So that would be u sub 1, and this is your u sub 2. This is at the beginning of the member, and at the end of the member, there would be 2 member end displacement. So that would be u number again along x direction. So you have u sub 3, then you number along y direction. So this is u sub 4. So we have identified the 4 member end displacement in the local coordinate system for this member M. Okay, we have to take note that B refers to the beginning joint of the member and E refers to the end joint of the member. What is the beginning joint of the member? So the beginning joint of the member is the joint to which the member end with the origin of the local coordinate system is connected. So for this member M, this is the joint, this is the beginning joint because this is the joint to which the member end with the origin. So this is the joint to which the member end with the origin. This is the origin, so this is the joint to which the member end with the origin for member M. So this is your beginning joint. So the end joint is this one. The end joint is the joint adjacent to the opposite end of the member. So the adjacent end to the opposite side of the member is the end of the member. Okay, going back, there would be, as mentioned, there would be 4 member end forces. So there would be 2 at the beginning of the member, and there would be 2 at the end of the member. So we're going to number again the horizontal direction as 1, followed by 2 on the vertical direction. So this would be Q sub 1. This is Q sub 2 at the end of the member. So there would be Q sub 3. Same procedure, you number along X direction, then followed by Qs of 4 along Y direction. So we have identified now our member and forces in the local coordinate system. So we have to take note, for every member, there would be 4 end displacement in the local coordinate system, and there would be 4 end forces in the local coordinate system. They are denoted by U and Q to represent end displacement and end forces in the local coordinate system. You have to take note that this end displacement and forces are defined relative to the local coordinate system of the member and are considered positive when in the positive direction of the local X and Y axis. So as remembered, our objective here is to determine the relationship between member end forces and member end displacement. So such relationships can be conveniently established by subjecting the members separately to each of the 4 end displacement as shown in figure C. So we have to take note, for every member there would be member stiffness coefficient denoted by K. Member stiffness coefficient K are the forces per unit displacement. They represent the force at the location and in the direction of Q required along with other forces to cause a unit value of displacement U, while all other displacements are 0. So now we're going to establish our member end forces, member end displacement in the local coordinate system, and this is being expressed as Q is equal to K times U. So this is now the relationship between member end forces, member end displacement, and member stiffness coefficient in the local coordinate system. Q, of course, represent member end forces, K represent our stiffness coefficient, and U represents our member and displacement in the local coordinate system. And Q, of course, there would be, for every member, there would be 4 member end forces. So they have Q1, Q2, Q3, and Q sub 4. And for every member, there would also be 4 member end displacement. So denoted by U sub 1, U sub 2, U sub 3, U sub 4. And we have identified that a while ago in our figure. And of course, to solve for the value for K, we have the formula. This is the formula for the member stiffness coefficient in the local coordinate system. So this would be E, A all over L in matrix form. You have the elements here. Of course, you have to memorize this one. So E represents, of course, our modulus of elasticity. A represents our area, and L represents the length. You have to take note that for K, for Q, for U, it is per member. For example, there would be 2 members in our plane truss. So you're going to have, if you're going to solve for member end forces in the local coordinate system, you're going to solve for each member. So for example, member 1, you can denote that as Q sub 1 equal to K sub 1 U sub 1. For member 2, Q sub 2 is equal to K sub 2 times U sub 2. And of course, for every member, there would be 4 Q, U, and of course your K is this value. You simply have to substitute that one. So then afterwards, once you have the value now for Q, for K, and for U, you simply have to simplify the equation using operations of matrices, and you can solve now for the value for Q, and whatever you have simplified corresponding to that, for every member you have 4 Q, Q1, Q2, Q3, and Q sub 4. Same with member 2. If there would be 8 members, meaning to say you're going to solve 8 member end forces using these equations that we have is introduced. So basically, that is the relationship between member end forces, member end displacement, and stiffness coefficient in the local coordinate system. So let's have a sample problem. The problem states that the displaced position of member 8 of the plane truss is given in this figure. So you are going to calculate the axial force for member 8. So for this plane truss, we are given with the displaced position for member 8. So the displaced position for member 8 is this one. So we are given with member end displacement. So you have here at the beginning of the member, so you have negative 9, you have negative 12 mm. At the end of the member, you have positive 12 mm and you have positive 16 mm. So those are the displaced position of member 8. So meaning to say, those are the specific value for our member end displacement for member 8. So our task is to solve for axial force for member 8. To solve for the axial force for member 8, we have to solve first for the member stiffness matrix in the local coordinate system, that is your K. So to solve for K, of course, you have the equation a while ago. You have EA all over L multiplied to this in matrix form. So you have to identify our EA all over L. E is our modulus of elasticity. It was given in the problem. A refers to our area. So get the value for the area of the member 8. L refers to the length of member 8. Since that was inclined, so you have to use Pythagorean theorem. So you simply have to substitute to this equation, and the resultant is 48,000 kilonewton per meter. And you have to substitute that onto our formula K, which is our member stiffness matrix, and you have now this equation. Then we have identified our member in displacement in the local coordinate system. So it was identified, you have negative 0.009, negative 0.012, positive 0.012, and 0.016. Those are in meters. So those are the end displacement in the local coordinate system for member 8. Then we have computed now, we have identified our K and U. You simply have to use the equation for member end forces in the local coordinate system, which is Q is equal to K times U. For every member, as mentioned a while ago, there are 4 Q and there would be 4 U. So you have identified Q1, Q2, Q3, and Q sub 4. This is for member 8 and equal to K. This is the value for K that we have solved a while ago. Multiplied to U, you simply have to substitute the value for U. You simplify this equation. So you have now your specific value for the end forces for member 8. So Q1 is negative 1008, Q2 is 0, Q3 is positive 1008, Q sub 4 is 0. Of course, for this first and second, located at the beginning of the member, third and fourth at the end of the member. Of course, the unit for this is in kilonewton. You have to specify the unit. And the member end forces are depicted on the free body diagram of the member as presented in the figure letter C. So we can identify that the end force for Q1 is negative. So based on our computation, Q1 is negative 1008. And of course, for Q sub 3, that is positive 1008. So therefore, our axial force is 1008 kilonewton and it is subjected to a tensile force. So member 8 is subjected to a tensile force. So that ends our discussion for our member end forces in the local coordinate system. So thank you.